Yeah, by the way, I'm gonna stream our school seminar to YouTube, but it's just in my personal account. Yeah, I'm gonna share the lecture video link in. There will be one section in my homepage as a group seminar. Yeah, by the way, I'm gonna stream our school seminar. Okay, I think it's streaming now. Yeah, Wenli, are you ready to
Okay.
share your screens?
Give me 1 second, sorry. Oh. Can everyone see my screen?
Yeah. Yeah,
Okay.
I think you should share some PPT or.
Yeah.
Okay.
So today, I'm going to present 2 papers. The first one is called the data-driven super parameterizations using the deep learning. Experimentations with the multi-scale Lorentz 96 system and transfer learning. So this is the main outline of the paper. I'm going to talk about the background and introductions, the multi-scale Lorentz 96 system and the data, and methodology and model, the results, and lastly, I will talk about the conclusion and next steps. So first of all, I will talk about the background and introductions. So as we know, if we want to make the weather and climate models computationally affordable, the usually way is use the physical base or the semi-numerical parameterization schema, which we call the numerical methods. And in other ways is the data-driven model. So in this paper, they have this 2 kind of different way to do the predictions. I will talk about these models later. And secondly, I will talk about the multi-scale Lorentz 96 system. So Lorentz 96 system is represented by these 3 equations. They are all the originally differential equations. So for the first one is to compute the last scale, which is like some wing, and also called the long wave in the atmosphere. And the F is the force term, which is the chaos in the atmosphere. And they also have the Y scales, the small scales, like the shock wave in the atmosphere, or the to turbulence. And they also have the Z represents the smallest scales, represent the gravity wave, which is smaller than X and Y.
Lin, I got a question. So
Yeah.
here you're introducing a set of ordinary differential equations, right? You got
Yes.
HK, YJK, and ZIJK. So what does those indices? What do these indices like K, JK, and IJK mean? Are they
So
like geolocations?
Yeah, K means their locations. If we have like this, I just draw if we have a map, we divide it into 9 parts equally. So this can be K1, K2, K3, something like that. So K is represent the locations. And in K1s, there are some Y also represents the can divide into 9 parts, but in the paper they divide into eight parts.
So you mean X are only modeling X, I mean X1 to XK and go on are only modeling the horizontal direction, and the Y are both horizontal and vertical?
The Y,
So because
no,
your Y's are indexed by two subscriptors, right? Like J and K, and X you're just indexed by K, right? And you got Z as actually have 3 indexes, I, J, K.
yeah. So yeah, like it just divided into equally. Like K have the in the paper it has 8K. So if so 8KX. So for one X, it has not AY. Does that make sense?
And for Z, how about Z?
Z also have AZ. For one Y, it has AZ.
Oh, I see.
So totally they have 512 Z. And what for Y, it has 64 Y. For X, totally have 8X.
Oh, so the K can still, I mean, if you just look at the K, it can still index some, like, you know, geological region, right? But inside the K,
yeah,
I mean, there might be some small cubic in the 3D space, right? I mean, for each particular K, you got 8 additional Ys.
Yes.
Okay.
Yes. Yeah. That's what I meant for drawing these scripts. Okay. Is there any question?
Yeah, I have a question. So for the first equation, like the left side is differentiate the X by K, right? And in the right side there is a X K minus 2. So what about like the derivative with respect to the X1? So if the K is 1 and then the left side is K1, what about the right side? Is K minus 1?
Oh, so if we start for the first one, like K equal 1, it will come like this is the K minus
1. Okay, so in the equation, the X minus 1 is just equal to X8, the last one, right?
The last one, yeah. Okay. Because we just the initial conditions, it was given by a fixed X. It has but in the paper is a fixed X. So they do have their own K. So does it make sense?
Okay, got it. Yeah.
It looks like for every smaller scale like YJK, it only depends on XK and lower level Z's, right? It doesn't depend on K minus 1. So they're kind of like only connect to its upper level variable.
Yes, only so one X only affects his own Y, and Y only affects his own Z.
Okay, so it's a ODE version. It's a hierarchical model of ODE version, right?
Yes. Yes. Any other question? Okay, great. So before I talk about the models, I will talk about in Lorentz 96 system, they have the two cases. They call case 1 and case 2. So case 1 is called the scale separations between X and Y. So X is representing the large scales and Y is representing the small scale. So scale separation means the such as like cow formations may change on the time scale or minutes to hours, and the large scales like wind may change on time scale of days to weeks. So respectively, those scale separations means the X and Y can change on same time scales.
What do you mean by scale separation?
Scale separation is like if the cow change like on a small scale, it will change very fastly, very quickly, but on the large scale, it will change very slow. So they're not on the same time scale.
Oh, okay. So it just means like a larger scale variable will change much slower than lower variables. Okay.
Yeah. So this the scale separation can determine by difference the coefficients to see if it is scale separation or not. So yeah, you can see the C is equal to A, and C here is equal to 10, H is equal 1, and H is equal 0.5.
Mhm.
So it can determine if the Lorentz 96 system is in case 1 or case 2.
So I have a question here. So X, Y are different variables. They are not the same variable that measures on different fidelities, right?
You mean the H?
The X and Y.
X
It
and
seems
Y?
like, yes, it seems like X and Y are different variables.
Yes.
Okay.
Yes.
And for the BC EDG, so I know there are constants in the ODEs, right?
Yes.
then-
Yeah.
And then there are only these two cases, like no other choices for the BEDG. They cannot be like 1, 2, 3.
Yes, you can. So only the coefficient equal to this value can be called case 1. If you choose the other value, they might call case 3, case 4.
Oh, there are 3, case 4. Okay.
There are some other cases also. So, but in this paper, they set this value to constant, which can make much easier for for testing or for sampling the data into the machine learning method. So does that make sense?
Yeah.
Okay. Is any other questions? Okay, great. Yeah, there's one more things before I talk about the modeling methodology. Am you guys familiar with the fourth orders Wunsch-Kalman methods? Is to compute the delta x, the next time steps for computing the next time step x, y, or c values. If you guys familiar with these methods, I can skip this slide.
You can just skip. This is just the most common used
Yeah,
ODE
for the
solver,
numerical integration.
Mhm.
So yeah, I will talk about the methodology and models. And for the first one, it's called the direct numerical simulation, the NDS. So it will compute the equation 2 to 4 with the RK4 schema, which using the time step is 0.005. Also is used for the training, validation, testing, and other models to compute the next time steps x and y z. There are also the different time scale. So the second model is called the high resolution. The high resolution, in these methods, they involve the variable z and the last term in equation 3. It only focus the x and y. So the purpose for this one is to make a cheaper model compared to the DNS, roughly 8 times less expensive. But it's still very expensive for practical use. Is there any question for these two models?
Yeah, for the skill separation case, I can understand that, like, you can drop z, right? Drop the equation about the gravity wave z. But
Yeah.
for inseparable case, will this high resolution model give similar accuracy as the base?
It will not as it's not accuracy as the base model. So they just like without this term and they don't care the variable z.
Mhm.
So they for these two equations they will only focus on like this.
So assume that because you use base model like the DNS as the standard, right, as the benchmark for training, validation, testing, I guess
Yes.
the high resolution are still has some discrepancy with the base.
Yes.
Okay.
Okay, I will move on to the third model. The third model called pairwise laws with revolutions, which is means they only focus the x. So this equation is from the original x, but we don't care the y variable. So instead we will represent we will replace this term with this term, and this term is computed by only x or some equations like the this is called the random process, and UP(x) was determined by this value, and this value was determined by the four-order polynomial equation. So you can see from this equation, they only have the x variable. And in this equation, this term 5 was the log 1 auto correlations, and the sigma is the standard deviation of the stochastic time series. And
Lag one
yeah,
autocorrelation is computed based on what? Based on x?
Yes, it's based on the last time series x. Like yes, last time. Pass some sigma. It's kind of like the auto regression equation, the first order regression equation.
Yeah, I'm curious to know how you calculate phi. My understanding is that you're gonna look at the sequence of x and you calculate the lag one autocorrelation, means that you just compute the correlation between the correlation between x1, x3, x2, x4, something like that.
Mhm. Yeah, the sigma, the phi and sigma was fit into the first order autoregressions.
Oh, it's fitting into the autoregression model.
Yes, yes,
Oh, it's the coefficient.
it's coefficient.
Oh, okay, okay.
Is there any question? Any other question? Okay, great. Let's move on to 4 and 5 models. So so this one is called the superparameterization. So it's kind of similar to the model I talked before, is called HR. So in HR models, I also paste the two different schema in the same picture, so you guys can see really clearly for the difference. So in HR model, X and Y compute their the next time step value separately, but in SR model, if we want to get the next time step X time the XT, we need to get from the YT. So what's that mean? Like we can see from the code, firstly, we need to compute the next time step YT, and we get their the Y values. So we can put into here to compute the next time X. But in the HR model, X and Y was computed separately. So this is the main difference. Does that make sense?
No, I didn't get your point. So, how do you do the super parameterization? You didn't replace any term here by some polynomial?
No, like if you look at the equation, this term and this term was only related to their own X and Y.
Mhm.
But for the SP model, X term, the Y term will be computed first to get the next time step Y. So this term is not related to its own Y value, but it relates to the next time step Y value.
But how do they, if it doesn't know next xt, how does it compute?
So
time step.
So it assumes so just like this equation is just do the normal differential integration something, but this SK is from the last time step. So the SK is from the initial value, but this Y value will change to the new Y.
Assuming they're gonna solve Y first, and assuming
Yes,
X is the initial
yes,
value.
yes. You can see from the code, it compute the Y first, and once he get the Y value, the next time Y value, it will put into the X for compute the next time step X.
But will they get, when you get X, will you go back to solve Y again?
The X vector will be it will be updated. Yes, the X vector will be updated and stored into some it will be stored and for next computing.
Oh, so you mean it's like alternatingly update, like I use current X, I solve Y,
Mhm.
and I use my Y to to substitute back to X and solve next step of X, and then I solve Y again. Is this like alternatingly compute XKT and YGKT?
Yes, kind of. Yes.
Why it is slightly cheaper than HR model?
I don't think he's cheaper than the HR model because we need to.
Oh, because you're every time when you solve equation, you're reducing the number of states.
Mm,
Okay,
yes.
but okay, but it's less accurate, right?
Yeah, it's kind of like slightly cheaper than the HR model.
Okay, this is another numerical method, right?
Yeah. It's still the numerical method. It haven't used the machine learning method.
Okay.
Is there any other questions for the SP model? I know there's the confusing if we just look at the graph, the map, the figures they given. So I also paste their code, so it's much clearer.
Okay. From figure now it's much more clear. The actual leverage is skew separation case, right? When you solve Y, you use delta T. When you fix Y, when you solve X, you use much larger step size.
Yes. They use the 10 delta T.
Okay.
This is much cheaper, so they didn't use the every time step. They used the 10 times the time step.
Okay.
Yes.
So the idea of the SP model is that the assumption is that the dynamics of the axis is much smoother than Y. The change much slower than Y. Okay.
Yes. Because it will compute the Y with delta T, but it will fit back to the X, but the X was computed with the 10 delta T.
It's interesting.
Okay. All right. I'm going to talk about the fifth models. For the data-driven parameterizations, so we already seen these equations from the PLR model, but in this model, this term will be computed it's computed by the ANN model, the ANN methods. The ANN methods, the artificial neural network was with the 8 hidden layers, full connection layers, and artificial function is ReLU. It was trained with the 1 million sequential pair of X and Y. X and Y was sampled from the DNS data. And we can see the cost is same as the PLR because in the paper he doesn't consider the computational cost, the times cost for the training.
I have a question about the number 5. So previously method 3, they have a Brownian term, right? So how do they add Brownian term in method 5?
The Brownian term?
Yeah, the eta T.
Eta T, okay.
Yeah, the method 3 says the eta T is a noise term, right? It's a random process.
This one? This one?
Eta T. Equation 6.
Equation 6. Oh, this one.
Yeah.
The eta T. Okay.
Yeah, so how do they add this term to the neural network?
You mean the noise, right?
Yeah, the noise in method 5. or method 5 is just a deterministic method.
I don't think they add any noise in the
Okay.
for the training.
Okay.
Yeah,
Okay.
they didn't mention any noise, but the next paper, the GANS paper, will add will emphasize adding noise, but I don't see any noise adding additions in this paper.
Okay, so
Is
they
there-
have a question about the method 3. Can you go back to the previous slide?
Yeah.
Yeah. So for here is so the goal is to learn the coefficients of the equation 7, right?
Hmm.
So the A1, A0 to A4.
Yeah.
So when you have the Brownian term in equation 6, so you can use the Archifour to solve this kind of dynamics. Standard Archifour.
Mhm.
Okay.
Yes, this coefficient was determined using the fourth order fit it on the DNS.
Okay. Okay. But you still need to use the Archifour to run the dynamics and get the final solutions to feed the data.
Yes.
Yeah. Okay. Okay.
Okay. Is any other question for model 5?
Did they mention how they train those models? I mean, how do they estimate those parameters, like in ANN and also in the polynomials?
So for the polynomial model, they just they given the initial x and y or c, sometimes have the z, but for the for ANN model, it just pop into the x and y pop into the like the x like kind of some, but just have the initial value, and the y only has the initial value something. So they put into a ANN model. X and y, something. An ANN model is used to learn the mapping between x and y.
Oh, okay, okay. So okay, you just use solver to get that term and y.
Yes. Yes.
Okay.
So yeah, if we need to do the predictions, we give the ANN to we give the x to the ANN, so he would get a y, or here we call the UPX something to do the prediction.
Okay.
Okay. Is there any other question? Great. And the last two model is also used in the machine learning methods. The paper proposed the data-driven superparameterization. So for the previous models, they already proposed in another paper. So in this paper, they proposed this model. So the narrative of this model is they use the RN model, the gate recurrent unit, to learn the time series change for the x and y. So, and once we get the well-changed RN models, we can do the prediction for the small scales. So this can call Y or small scale because why we call small scale, because it can also represent the smallest scale, the Z value as well. So, but in the training they didn't use any Z variable; they only use the Y. So sometimes we can call it Y as well. So this RN model was trained with 1 million sequential pairs of C and Y, and the C and Y, X and Y was sampled with from the DNS data. And we can see it's 88 times cheaper than SP and the same cost as the PLR and DDP. Any question for this model?
Merlin, can you see, I would like to see the original formula, original equation for XT with your OPXC.
This one.
Yeah, the equation too. Oh, it's a summation of all YJKs. Okay.
Yes. Yes.
So okay,
So
I know that when they create the training data, they're gonna summation the solved Y across J and get B and times HC and divided by B to get their training output. Your current XK will be your input, and we'll
Yes.
get the sequence of XKs and the
Yeah.
summations. You got
Yes.
the GPU model. Okay.
Yes. Yes.
Yeah.
So in machine learning models, they just replace this term by using the machine learning model for prediction.
Yeah.
But this term still using the numerical integrations for compute the large scales.
Okay.
Is there any other question for the model 6? Okay, great. So lastly, I will talk about the fully data-driven model. So for this model, they only they only train with the X. If we have the X1 to Xn, we put this sequential data into an RNN model to run the X on different times, the mapping from distant time. So, oh, sorry, this should be called XT. So we can do the prediction for just because I only learn the mapping X1 to, for example, X1 for the next time 2 and XT minus 1 to the next time X. So I only learn this mapping. So they kind of very roughly learning for the machine learning. So we can see the accuracy is not that good as the previous models. And they also use the 1 million sequential value XT. And the purpose was a complete data-driven model for predicting the system evolution.
What about the Y and Z? So they are not a variable of interest. So for this this task, so solving the Lorentz system, we only care about the X.
Mm-hmm.
Okay.
They only care about the X. They use the historical value X to predict the X.
Okay.
Yeah, like I said, why they're here just only consider X.
But we
But
can
they
also use RN to model Y and Z. But they just since X is the only variable of interest, they just model X. Okay.
These are two different models because in this model, RN is to learn the mapping X to Y. But
okay.
in this model, RN learn the time step from next one to the next order, next time. Yes.
Okay, makes sense.
Is that any question? Yeah.
Yes.
Go ahead.
And how do they represent the first term? The F is a constant or a equation?
The F is equal 20, in this for the training and evaluation. Yes.
Okay, so they put it as a constant. Okay, thank you.
Yeah, the F is constant. The F is constant. We will talk about later because the paper will change the F because F is the chaos term or the force term. It kind of you know in atmosphere model, the initial condition might change very largely for the result. So they changed the F to experiment to see the experiment with the other chaos. Okay, we will talk about this term later. Is there any other question for the models?
So when the method 7 published?
When the 7 model published?
Yeah, the 7 model. So when the paper published? So recent paper?
No, you mean this one model?
Yeah, this model. Yeah.
I don't know. I didn't see the.
Okay, that's fine. I'm just curious.
Maybe this one model is also, you know, just for comparison. Nobody published before.
Okay.
I haven't looked at the citation details.
Okay. Yeah.
Is there any other question for the models? Okay, great. And next, I will talk about the results. So once we had those models, they just for the first matrix they use for experiment the short-term spatial temporal forecasting. There's also two conditions. One is without the noise initial conditions. So the prediction accuracy for all model for case 1 and case 2 is compared. And we can see HR model performance the best among the NIMBLE models, and SP following closely behind. And BLR has the shortest prediction horizons, which just means PLR model cannot do a very good prediction in the short-term spatial temporal. So accuracy we can see in, but these 3 models are the NIMBLE model. We haven't compared to the they haven't compared to the machine learning model. And HR and SP are computationally more expensive than PLR. And the data-driven model, DDP and DDSP with the low computational cost, but performance slightly better than PLR. And DDSP performance slightly better than DDP because they use the different machine learning model. In case 2, DDP performance decreased compared to PLR, while the DDSP still outperform PLR. And the fully DD model accuracy is similar to the PLR model. So the accuracy is kind of like the same.
So DDSP is the one you use GRU to model the term, right?
Yes, the model GRU models. Yeah.
DDP is use a neural network, use artificial.
The artificial neural network, yeah. And DD is used the historical X to predict the X.
And the PLR is using the polynomials.
Yes, polynomial. Yeah. It only consider the X value.
Okay.
The small scale is represented by X as well. So. And second matrix, they use the with the noise initial conditions. Oh, sorry, Shibo. They do have some noise injection. Sorry, I didn't. I might can't well remember the experience. And the experiment was the same as the noise initial conditions with the without the noise. Sorry, I should write a note without the noise. And expect the prediction Harrison for all model decrease because it had the noise. So the accuracy, but more so for the more accuracy models. DDSP advantage become even more apparent, especially when compared to PLR and DDP. And in terms of the computational cost, the DDSP provides performance slightly similar to the more expensive SP model. So, which means DDSP has the a better accuracy, but is lower computational cost than the SP. Is there any question for the first one we saw? First we saw?
Hi. So I have some
Yes.
question about the performance. So, in the method, it seems that for the DDP and it used the PLR to estimate the Y value, but in the result, actually DDSP outperformed the PLR. So, I didn't understand that.
You mean this one?
For the first one, without noisy initial condition, yeah. So
without
for
the noise, okay.
Yeah, for the performance, for the performance, it seems that the DDP outperform DLP, PLR, right? There are
This
two
one.
methods.
Kind of
Okay.
get lost.
Yeah. So I mean, when you introduce the method, you mentioned that in the Y step, it used the PLR, the low resolution parameters to get the data.
No. They use
Not.
the
Okay.
DNS to get the training data. So
okay.
PLR
so could
model
you go back to
Yeah, PLR model is compute only care the X. Like this term is
Okay.
only compute by X. So they did this model doesn't care the Y variable. Like I say right here, only focus on X. Sorry, I'm kind of confusing. Sorry, I make you confused about this. Sorry. Does that answer your questions in this one? So PLR model, because we DDP and DDSP use the machine learning model to learn the mapping X to the Y. So it only consider the Y variable, but PLR only consider the X.
Yes.
So this is the reason why DDP and DDSP outperform the PLR model.
Okay. Yeah, it makes sense.
Okay. Is there any question? Any other question?
Overall, is DDSP is more accurate and more robust to the initial condition.
Sorry, can you repeat your question?
Yeah, so overall the DDSP is the
robust. Yeah, it's robust. Yeah.
Okay.
Is okay. Other questions? Okay, so we talk about the short-term forecasting. So second one, they have the second one, they have talked about the long-term statistic. So in this experience, they we produce long-term system statistic, which is they use the PDF, the probability density functions to see the long-term predictions. So if we see this graph, this kind of maps, we can know they only focus the tails to see if this model can do around long-term predictions. So for case one, all model except PLR, all the model can produce accurately system long-term statistic. And for case two, only DDSP and DD model can accurately reproduce the system statistic, particularly the tails of the PDF.
What is
for-
DD model?
Oh, sorry. Go ahead.
Well, what is DD model?
DD model is the fully DD data-driven. Only case the
okay.
history X.
R1.
Yeah, sorry. Not sure. R and then X. So this one is the R and then X and Y. Okay. Any other question? Okay. Next is the generalizations to the system with the higher F. So like I said, they were trained and experienced on the F equal 20, but they want to see what if we have the well-trained models and with the slightly a small data set with the F20 F equal 24. We want to see the machine learning model performance. So they make some experience like they're using the transfer learning. So DD models, the short-term prediction accuracy improved, and the generations gap for DDSP and DD was closed. So we for this one, actually I didn't see how accuracy they improved. They just say in the paper the generation gap for DD and DDSP were closed. Yes. So
What does it mean for transfer learning? Where did they just use model trained with F20 to F?
yeah, they get a model. They just directly use the training model, the training model on F equal 20, and they use another data set, a small data set to do the fine tuning of what we call field shot. To
They just use the new data to fine tune the trained model.
Yes.
Okay.
You know, here they use a million data sets, but next, yeah. Is there any other question for the full result? Yes, the F is represents the chaos or the first term we call in the atmosphere model. So conclusions, we can see the paper, the author, they proposed a methodology called data-driven superparameterizations, and to lower the the computational cost as the low resolution model. And in performance, the DDSP outperformed the PLR models in predictions, both short-term change and long-term statistics. And they found the DDSP is more efficient than the SP model, super parameterized model. And about the generalization, all the models generalize well on case 1, but some models struggle in case 2. So they use this transfer learning to improve the generalizations. And we also they also consider the PDF when we look at the examine. So they say it's not efficient only look at the PDF, but when especially when we they need to focus on the tails. Lastly, I will talk the next step, the eliminations, the future testing. So because the Lorentz 90 system is a simple hemisphere system, they want to see how these models can perform on a complex model like the 2-layer models. And they also see the hybrid models is very is not stable. So they want to do some more research when apply the DDSP to see the performance in the stable. And lastly, they also propose another machine learning method using the GANs to do the hemisphere for hemisphere model to do the hybrid models. We'll talk about this model for.
What's the meaning of the instability? You mean run the numerical integration for other models, it can cause numerical instability? Or just those models, this other system can be unstable in nature?
I would say the other hybrid model is not because the DDSP and DD model discussed are stable. It's not include these 2 models. So the other hybrid model means the DD model, I think. Sorry, I can't mess up this.
But what do they mean? What do they mean by more complex system? Because you train DDP, DDSP, and DD are in this multi-scale Lorentz system, right?
Mm-hmm.
Did they train the same types of models in another system? They concluded that other hybrid models have reported numerical instability.
No, I don't think they included the other models in the instability.
But how do they conclude that? Like other hybrid models have reported numerical instabilities in more complex system. So, I mean other hybrid models like LPR has been
because I think the hybrid model means we both use the numerical methods and the machine learning models combined can call the hybrid models. So I don't think the PLR model is the hybrid model. The other hybrid model might be the other numerical method plus ML methods, but I don't see they specify the hybrid model.
Can be other models, not in the seven models you introduced here.
I think so.
Okay.
Yeah, because the first center is always said that DDP and DDSP was discussed as our stable. So I think the hybrid model, they didn't mention this specifically.
Yeah, let's move on to the next paper.
Sorry, can I go to the restaurant for a few seconds? Sorry.
Yeah, sure. Yeah, this is a very interesting work. It's simple, but it shows that how like people. This is some paper published in an atmospheric journal, like how those guys like using data-driven method to reduce the cost, right? Especially in multi-skill physics problems. It seems that their method is effective, right?
Yeah. Yeah. And I think the instability issue can be solved by put some constraints on the neural networks or the RNNs, like the neural flow does. So the neural network and the RNN should be Leibniz continuous something, then that instability issue can be resolved.
Yeah, of course. Yeah. The problem we can think about that. So we see this is one example of multi-skill physics system. So where each skill corresponds to maybe one set of equations, right? And different skills are coupled by a few terms in the equations. So if we connect it to operator learning, right? Can we do some like multi-skill operator learning? And maybe we have some like operators at different skills, and the different neural operators are interacting. Yeah, this yeah, we should think about, because I didn't see that in the machine learning literature. Yeah, maybe those scientific computing guys have already started doing that or thinking about that. What's your idea? What's your thought?
Yeah, so I think the difference of this problem from the previous multi-scale and the multi-fidelity problem is that it has the X, Y, Z. Actually, they have different physical meaning. So, and they follow the different equations. So I think if we are trying, it seems not easy to apply the previous multi-fidelity or multi-scale method here directly. So
yeah, this is not a multi-fidelity. I thought this is multi-fidelity at the beginning, but I saw the X, Y are different variables. So
yeah.
So it's not, but we can build different operators and find a way to couple them together and learn the correlation between them.
Yeah, makes sense. So, or I'm thinking, is that possible to build some graph for this problem? And currently, the performance is bad to estimate X, the large scale X directly. So maybe there is also some opportunity to improve the X with neural network directly. So making it to be the for data driven method.
Yeah, I think so too. The number method, the number 7 is too simple. We just use the RNN to model X directly, but there must be some hidden variables there, like the Y and Z, and they could be incorporate them into modeling X should be improved the performance.
Yeah, so actually I'm still I didn't actually I still a little confused about the Lorentz 96 system. So what are those system? What's the application of this system trying to solve? So is that to just predict some climate or predict some yeah, actually, is there some specific example for this system?
It's just a pedagogical system to show chaotic system, to show chaotic phenomena.
Sorry, guys.
Yeah, please,
Okay, guys. Okay.
continue. Yeah.
Sorry, guys. The next paper is called the machine learning for stochastic parameterization generated a rosary network. Also, we call GANs in machine learning. Also, like the last paper, I will introduce I will talk about the background and introductions, the models, resource, discussion, and conclusions. We already know the background from the last paper, and here they just say we cannot eliminate some resource subscript process. A method called stochastic mappers. It was initially proposed for the European Centers for Middle Range Weather Forecasts. So they just want to. They say if we want to see the performance if we combine the stochastic model into the weather and climate model forecasting. So they use the GANs for the stochastic parameterization. We also know the Lorentz 96 system from the last paper, but they didn't list the Z variable in this paper. I mean, they don't consider the smallest scales in this paper. In this paper, they set the K, which just means they have 8 x per x. J means per x equal 32y. They have 256y in total.
Also, each x is corresponding to 32 y variables.
Yes. The number of y variable per x is 32.
Okay, so slightly different from the system you just described in another paper, right?
It's divided a much smaller scale. Divided a much smaller, if we have the 1x, 1y, 1x, they divide into 32 parts.
Okay.
X is 1. The spatial scale with B is equal 10. The temporal scale C is equal to 10. The Frossington F is 20. For the Lorentz 96 system. In this paper, they also have the and the variation data for the DNS for the GANs. So they use the second order Wunsch color, which we can see from this this equation. This free equation, this term is represented by this equation, but they use this equation for only for prediction. They use the original these two equation for get the training data predictions, because we want to compare the prediction performance with the GANs. So for computational lower computational course, they use the second Wunsch color methods to do the predictions.
I didn't understand your instruction here. So what do they mean here? Like which are instead parameterized? Why do they truncate model? Your signal is not very good.
Like this for prediction, they only use the X value for prediction. They consider the Y for in the predictions, which just mean use the X to represent the Y. This is called
If they use the numerical method, why do they need the truncation? It's just the simulate, right? Just to do the numerical integration.
Use the numerical integration, but for the prediction, they didn't the Y value into the last term.
So you mean is their method? Is there a GAN method? This is how their GAN method is doing?
This is not the GAN method. This is only for prediction. Is to predict the small. This is called the smallest, the smaller scale, the small scale. It just also use the GANs to predict this one, but in this model, in the Lawrence 96 system models, for the prediction, the paper used this term is to by this term.
So yeah, you need to let us know. Is this U hat in equation 2 the term that their method learns, their GAN-based method learns?
No, yes, this term is GAN method learn, yeah, to do the prediction, but GAN's method learn X and U as well.
And
So
then when they do the prediction, how do they do that? They just solve the numerical integration into.
yes, they solve the numerical equations. Yes. Sorry. Yes, because they don't use any Y here. They use the U for put. They use the U put into the GANs for training, S and U.
Yeah.
So
yeah.
it represents the small scale. Yeah.
But how does it relate to the so-called truncation?
So-called truncation.
Truncation. What do you mean by truncation?
Truncation means
Does it mean that they don't have the dynamics of Y?
Yes, they don't have dynamic y. Instead, they represent the y with the u, but the u is can compute by this equation. I think
So
the
this is how they get UKT, right? They use that to train the GAN.
yes.
Okay.
Because they replace the y with this one. I think the reason is this xt is the forecast estimate of the SKT, and u SKT is the parameterize the subgroup tendency. The subgroup means the small scales.
Mhm.
So I think that's the meaning of the chain casting.
So, I mean, equation 3 and 4 is just telling you how do you get the training data for UKT. And UKT,
Yes.
Ah,
UKT is then learned by the GAN, by some universal neural net.
wow.
Is that true, Lin?
Yes, because GANs want to learn the x and u was computed by this equation. So the GANs want to learn the mapping x and u. He want to learn what kind of x can produce what kind of u. Does that make sense? And u here can, so it give with the y. So he want to use another way to present the to compute the prediction.
Yeah, let us look at how they design again.
Yes, so because in GANs he want to have two inputs. One actually is three inputs, but we will talk about the last input is not related to this value here. So he want to learn the x. So we already know what x is, but u here is the prediction, is the computed by this equation. So no, the x, this term was computed by this equation. So what's that mean? Like you want to do it's kind of like the last paper model DD, but oh no, the PLR model. He want to just only focus on the x and use the x to get the predictions.
Yeah.
What is the?
You need to tell us which term they want to predict with GAN, and how do they get the training data of that term? Just answer this question before we get into the detail of GAN.
Okay, this term is put into the GAN for training. So if we have x, so we can use the x for prediction. We can use the x into this equation to get the u.
And then then they train again to make prediction of u. Even
Yes,
x.
yes, they want to use the GANs to train to get the next time step u, but yes, the generator, yes.
But why do they say this can be estimated? It's not. It's just a approximation, right? It's not an accurate term.
Yeah, it's just an estimate value. It's not the accuracy value.
Why?
Because they do the prediction is using the the delta t right here, delta x right here. We can see this one is delta x, right?
So this is actually derivative of x.
Yes, the u is represents the small scale, but this term is represent the current statics, current state, it to minus the
Oh, okay, I see. Okay. Yeah,
Kind
you just derive that from 2, you get it's 4.
Mhm. Because this term is include the large scale and is included all scales, this term. So he want to minus the x scale, so we can get the delta x to get the small scales.
And they use GAN to make a prediction because they kind of ignore the underlying physics, right? So they model it as like stochastic model.
Stochastic model, yeah.
Because I mean, if you know the underlying physics, I mean, y thing, you'll be able to compute uxy as 3, as equation 3 says, right? And now they just want to use x. Okay, so they want to use approximation of UKT to train again. So that's why they got a stochastic training, because GAN is generating some stochastic samples.
Yes.
I want to
Yeah.
clarify it. So, they use the GANs to simulate right turns of equation 2. Is that correct?
They
Because-
want to use the GANs to make the small scale prediction. They don't predict the x, because we will see the details in later, but I haven't, because next I will talk about the GANs, how to do the prediction.
I have a question. So what is the equation 3 used for?
Equation 3,
because you already used the equation 4 as the ground truth of UK. So what is the
I
equation
would
3
say
used for?
equation 3 just to tell you, just tell us u x and y, u x and y is represents the small scale.
Okay.
Originally is represents by this term, right? This term we can use this term to represent, right? In the original Lorentz 96 system, but he want to do the estimation with this equation.
Okay, so in the climate task in general, so the data is given by a series of x, observation of x, not observation of y. So we don't have observations of y in general.
In general, yes, because we don't need y for training.
This seems not.
Yes, so the motivation is like this. So they create a simulation system to show their performance, but in practice, they measure x, they want to predict x. They know that underlying x, there must be some smaller scale physics, which they don't know. So they approximate this u hat term by this equation 4. You see that equation 4 is just derived from equation 2, nothing else.
Yeah.
So they believe that their hypothesis is that, okay, I'm going to train again to make such a prediction to fill this gap between x and some low-level physics. But they tell you in their simulation system, the actual gap is equation 3. You're gonna measure, okay, your GAN's prediction and also your 3, the ground truth, to see whether it can recover such gap.
Okay.
Yes.
Can I ask one question? So, when we talk about the large scale and the small scale, it's always about the time, not the space scale, right?
No, large and small scale is about the base. Because
It's about the space.
it's about the space.
Okay.
But we talk about they have the two cases. Two cases mean on different time, like they happen on different time scale. Here scales
X
means
and Y
the-
are spatial variables, right? X and Y are spatial variables.
spatial.
Variables.
Yes. Because sometimes they use the weather to represent the small scale, the client to represent the large scales. Does it make sense?
Okay, then so I mean there should be some observation in small scale. So
No.
I'm just
There's no observation in small scale. That's the problem. Or it's very hard to collect smaller scale observations.
Yeah.
okay.
One constraint is maybe the data is hard to collect. Something.
Okay, so the equation 3 in this setting is useless, right? So it cannot provide any observation, or it will not be help the network to learn better.
Yes.
It's just used to tell you this is some ground truth, but when you train again, you need to assume that you don't know that,
Yes.
so that you can
Okay.
do some comparison.
Yes.
Then-
Compared to go ahead.
I get that. Then what's the motivation for the Y and Z term in the original
The last paper?
in the original last paper, or in that system. So I believe they have some motivation to propose that equations in that way. So
So the motivation is they want to make the computational cost lower.
okay.
Yeah, they don't
They
care
just-
the. Yes, actually they don't want to compare the accuracy, because you don't compute the Y and see the small scales. It's hard to compare the accuracy because they are not on the same data level, you know.
Okay.
Does it make sense? Okay.
Yeah, thank you.
Yes. So yeah, the one thing I want to say, these two papers, they just want to focus the computational cost. Is there any other question for the Lawrence 96 system in this paper? Okay, great. Let's move on to GANs. Yes, so as we said before, the input of the GANs is the X, last time step X and K location, and the U, last time step U, and on the K location. So we cannot see any Y because U is the prediction value or the estimate value. And the Z, this term is called the latent Gaussian random vector, kind of like the noise ejections. And there's for the discriminator, they also accept the U and X and U. The V value is the maybe the either UTK which is mean from the training data or from the generator. And the output of the discriminator is the probability that VTK is come from the training data or not. And GANs, both generator and the discriminator have two hidden layer with 16 neurons, and use the salute functions and L2 regularizations. So the purpose of the GANs is to produce the data that looks like real data. And discriminator is trying to discriminate if the data is real or generated. So for the noise injection, in this paper, they use the white noise and red noise. So white noise is sampled from a standard normal distribution with the mean of 0 and the standard deviation 1. And the white noise is generated by the following equations. So we can see the 5G, this term is the real data minus the estimate data, plus the last term real data minus the estimate data, and we get their expect values and divide by sigma function sigma square. And the sigma g is computed by the 1 minus 5g square and over 1 over 2.
So what does the U hat TD mean?
U hat TD. This term means the estimate value. It means it's generated by the generator, I think, because we can see like this one is from the training. If we have the head for the U is from the generator.
So this noise injection was applied in training, in both training and test.
Yes. I would say it's just for training.
But in test, how do you predict? I mean, predict you're gonna inject noise as well, right? So inject the white noise or red noise.
So he have multiple GANs. Some GANs have the noise adjustments, but some GAN with the white noise and some GANs have the red noise.
So it's just a test. Which one is better?
Yeah, just have what kind of GAN have the best performance.
Okay. Okay.
Yes. Yeah, we can look at the table. You can see this is all the different GANs. Some GANs have the 2 input layer input variable, but some GANs only have the 1 input variable. And they also set different noise magnitude for testing. And noise correlations, we can see some GANs use the white noise, but some GANs use the red noise.
Oh, okay. So they train a zoo of GANs, and
Yes.
the test that they choose when they inject noise, they choose different noise magnitude, and see which one is better.
Yeah, which one is better on the weather and climate forecasting is better. Yeah.
Okay, so when they do the prediction, I guess every time they run a Miniputa, what they call again, they inject some kind of noise and make prediction, and then they continue the integration, right?
Yes.
Yeah.
We will have the other model for the benchmark for see how the GANs performance.
Okay.
The full model I will talk about later. And the output layer noise is optional. We can see from the generator, this one is optional. So the paper want to see if in the last layer if inject some noise, if they have the better performance compared to no last layer noise output layer.
Okay.
Yes. Is there any question for the GANs?
So in the original GAN, there will be only a noise inputs to the generator. Now they have the XT and the UT as the connection. So it's so VTK is the ground truth.
VTK
Is a prediction. Is a
So the prediction as well. So that makes sense. Okay. So conditional.
VTK means he either can be training data or the data from generator, the prediction from generator.
So did they say why they use GANs instead of VAEs? So VAE can do the same thing, right? Other models, why they use GANs?
They don't actually. They just they just put in a random, not random, like seems reliable machine learning model put into it and to see how's the performance. Maybe they can use the other model to see how's the model performance in the atmosphere models. They can use other, but they didn't say why. So GANs only offer a front framework because they want to use the stochastic parameterization. So GANs can provide the stochasticity.
Yeah. Oh, okay. So I guess the basic idea is that they just want to, given X and U, they want to generate a distribution over the U instead of, okay.
Yes, because compared to other models, some model they have the deterministic parameterizations, but after they get the deterministic parameterization, they add the stochastic. But in the GAN, they can embed the stochastic, the randomness in when they training the model, when they train the model. So I think that's the main difference. Why they use GANs instead of the other model. Does it answer your question? Do I answer your question?
Yeah. Yes. So when this paper get published?
Is 2020. In 2020.
Okay. Yeah, before the diffusion model.
Yeah, before the stable the diffusion model. Yeah. Any other question for the GANs? All right, let's move on to some training details. So if we get a branch called B, we split it in half. So one subset will directly feed through the generator G, and after they get the estimate or the prediction, they feed into the discriminant D. And the other subset just directly sent to the discriminator. And here is the loss functions for the discriminator. If you guys familiar with the GANs, you guys know why they have the two expect values, because if we only consider this term is for the discriminator, but if we want the generator and discriminator in the balanced situations, we don't want the discriminator too powerful or the generator too weak. So we want him to imbalance, we need to consider both in the discriminator. Consider both in the loss function. So, and this one is the generator loss functions. And the GANs was trained, the wave was updated through the stochastic gradient descents with the bench sets 1024. Learning weight is 0.001 with the Atom atomizer. The GAN are trained on 6 million samples and evaluates on 29 million samples from different portions of the true ones. And in the first 20 epochs, so they totally trained 40 epochs. But in first 20 epochs, the wave are safe for analyze every epoch. And after 20 to 30 epochs, every 2 epochs, which we save the wave. And the GANs was developed with the Keras v2.2 machine learning API and the TensorFlow v1.13. Any question for the training details?
We can just skip it. It's pretty standard.
Oh, okay. And the third model is the benchmark against to test the GANs parameterizations is called the polynomial regression parameterizations, which is similar with the PLR model in last paper. So as we said before, this term is represent the small scales. So it used like the last paper, the PLR model, it used 2 terms to get the estimate values. So the first term is computed by the qubits polynomial functions, polynomial equations. And the coefficient ABC are determined by a least square fit to the SU data from the Lawrence 96 true running. And this term is the noise terms, and the coefficient is also fit by the first order autoregression parameters fit from the residual time series. And this term are the independence for different x values. So we can see that this term is sampled by the distribution with the mean 0 and the standard deviation of 1.
So
any question for the
when in the training, their U hat is still estimated, like
yes.
Okay.
Still estimate, yeah. But this one is slightly different for the first one because it's used different equation for the estimate values. Is there any question about this one? Okay, great. All right, let's get into the result. So there's 2 matrices. The first one, they assess the accuracy of the weather forecasting by using calculating the root mean square error, and lower RNSE means the higher prediction accuracy, and the kind of the Lawrence 96 system can simply define as the PDF of the individual XTK value. So they use the inheritance distance to measure the difference of each forecasting model. We will see some details later. The second result is the offline assessment of the GANs performance, which means they they get the value chain gains. They want to see how they how's their performance on the predictions. So most of the gains shows the gradual decrease in the inheritance distance. So we can see they are all decreased, but only like the gains with the input have two inputs can typically performs better only use one input. And the third result is they want to know the noise standard deviation, how it affects the Klein model. So they similar the graph like this. We can see this is the true graph. So the highlight on the certain means the most of data on the centers. So we can see some model like this one, and this one. They didn't they don't have the good performance on the Klein model predictions. But like this did well on the prediction. And we also see some the shape of the true model compared to like this one, we have the actual prediction. I think the GANs can predict the value they haven't seen before. So just for the client models, for the client forecasting. And any question about these two we saw?
What's the meaning? What does it mean by like gradual decrease in Hallinger distance? What does it mean?
This
I don't
one?
know. Yeah. What does it mean? Like for if you observe a gradual decrease in this Hallinger distance, what does it mean? I mean, it kind of deviate from the.
It means because they generate the predictions on the forecasting. So if we compare to different scans, the forecasting distribution, we know compared to the ground truth, they have the decreased tendency.
So I mean along with the, what do you mean by epoch? Epoch means the training epoch or
the training part, I think. If we training
so I mean along with training, your forecasting sequence is closer and closer to the ground truth.
Yes, I think so.
But this is just telling you the difference between your prediction on the training sequence and the ground truth, right? Or is this about the test, the generalization performance?
I would say the GANs only compared like for all those different GANs, they didn't compare each other. They compared to the ground truth. If their distance slower means they estimate is more accuracy. It's more accuracy. Yes.
Yeah, this estimate is more accuracy in some test sequences, right?
Test sequence. Yes. Yeah, if we
in section 3, I mean, in GAN simulation of subgrid skew tendency distribution, they're just showing like if you use GAN to simulate whether those variables have the similar distribution about the original system. Okay, that makes sense.
Yes, because they want to compare on different standards. They both compare to the ground truth, but just compare once is in using the inheritance distance to see how they estimate accuracy. And this what we saw is to see how the distribution, how the GANs can capture the shape of the real distribution.
Okay, how much slides are left?
Four more.
Okay, I think we can stop temporarily. We will go back at the 12:40. Yeah.
Okay.
Yeah, wrap up your slides quickly so we can let Hao Zhe to start with his introduction about sequential Monte Carlo. So we'll continue on 12:30, 12:40.
Okay.